Now we are dwelling deeper into the more specialized parts of organic chemistry, and this part is quite exciting. This will be probably longer than the previous topics because it's a lot of structures. The topic for this point in time is stereochemistry. Okay, so stereochemistry talks all about isomers, and isomers are two or more compounds which have the same molecular formula but differ in structure. Alright, so there are two types or two ways that they could be different in structure. The two terms I'm going to use at the moment are going to be customized in definition. I made my definition for this just for making discussion easier. So the first term is arrangement and the second is conformation. I think it would be better, we would better understand this later on, but just as a summary, arrangement is the actual bonds between atoms, and conformation is just the spatial differences, so or the 3D appearance of the bonds. Alright, so we're going to tackle these two terms as we draw a table here. First of all, we could classify isomers based on if their difference in structure is by arrangement. I'll just use the A here, or space. Alright, if the difference is arrangement, you call that constitutional. Okay, how would you say there is a difference in arrangement? We say we say arrangement is talking about the actual bonds. For example, I have this is what's in the handout, C4H8O2. Right, I have three formulas drawn there, and they all look something like this. Look at this. This one is different from this because look, the oxygen here has two oxygen to carbon bonds, right? This is the first oxygen to carbon bond and this is the second, while here the oxygen has one oxygen to carbon bond, which is this one, and one oxygen to hydrogen bond, which is this one. There's already difference in arrangement or the actual bonds. These are the actual bonds I'm talking about. Okay, and here furthermore, look, here we have a parent chain without any substituent. In here we have a substituent. Even in that kind of arrangement, or even in that sense, there's a difference in the bonds, and we could say that that's also a difference between this one and this one. So meaning they are all constitutional. Alright, as opposed to the spatial isomers or the stereoisomers, most likely the two isomers have the same actual bonds. For example, here I'll draw this ICLBRF. It's my favorite example just to make things quick. Alright, IBRFCl. These have the same actual bonds. This one in this molecule, in both these molecules, we have all of the same bonds. One C to I bond, one C to Cl bond, one C to bromine, and one C to fluorine bond. So it's all the same. The only difference is I said that this is the 3D formula, right? The line dash wedge. This is the spatial difference that we are talking about. So it's less drastic, so to say. the difference between them is less, is less as compared to that of constitutional isomers. So that's the difference between constitutional and stereoisomers. Alright, now we could further subdivide constitutional and spatial isomers into more specific types. So we have 3 for constitutional. If the difference is in the parent chain length, skeletal. Let's have an example of a skeletal isomers. Alright, I'll use this paper. We know that this is the parent chain simply because there is no other way to assign the parent. It's a straight chain compound. So here we have 1, 2, 3, 4, 5 carbons in the parent chain. If we have here also 5 carbons, but the parent chain now, how many? Only 4. The other carbon becomes a substituent. These are skeletal isomers. Alright. Now, the next would be the placement or the locant of the FX group, functional group. Okay, I'm reading kasi the table in the handout. We call this positional because we're talking about the position of the functional group. So I said the locant of the functional group. Let's have 2 isomers with a hydroxyl functional group. Alright, this one and this one. So how do we assign locants? Locants again, here lowest sum, so we start here because we'll land with 2 if we do. And here we start here, of course, as number 1. So here, the locant is 2. So this is 2. This is 4 atoms, butanol. And here, the OH or the hydroxyl is in 1. So this is 1 butanol. This is what you call positional isomerism. Now, the third type is if the difference is the actual functional group. That's, well, obviously, the name is quite common sense, functional. Alright. For example, go back to this paper. For example, I draw ethanol. And I draw this. This is actually an ether. This one has the hydroxyl functional group. This one has the ROR. This is what you call an alkoxy functional group. So the functional groups are different, but if you count the number of carbons, 1, 2, 1, 2, the number of hydrogens, 1, 2, 3, 4, 5, 6. Here we also have 6, 3, 3. And the number of O, we both have O each. It's the same molecular formula. So these are isomers. Different functional group. These are functional isomers. Alright. So those are the 3 general types of constitutional isomers. Now we go to the spatial isomers. Alright. So here, I'm going to assign 2 new terms. Here we use the word configuration. Here, the conformation. Alright. When we say configuration, the spatial difference between the 2 isomers can be overcome, meaning that one isomer can be the other isomer only by breaking the bond. By breaking a bond. Here, in the conformational isomerism, all you have to do is wait for a period of time, and it will naturally, one isomer will naturally become the other. All right. So let's make a different. Let's see the difference here. I'll go back to this example. Here, remember, these are sigma bonds. These are very strong. Let's talk about the point of difference between the two. In order for this isomer to become like this, you have to break these two bonds and then exchange them. And that's where you make this look like this. So since you have to break a bond, we say that these are configurational isomers. Alright. And there are two types. This one, since these are tetrahedral in nature, we call these isomers as optical isomers. And we will know why they are called optical isomers later on. Well, the other type of configurational isomerism is, look at here, you have to break a sigma bond, right? Here, the second type, you have to break the double bond. So actually, this second type applies to two cases. The first is if it has a pi bond, alright, and the second case is if it is cyclic. Alright, let's draw an example. No, I'll change this one. Chlorine, H. The consequence of having a pi bond here is that it keeps the substituents of these two carbons in place. What does that mean? If, for example, I want to rotate this in a way that chlorine from this carbon goes down, the carbon here joins the rotation. So if the chlorine here was at the bottom previously, since you rotated this in this manner, the chlorine would also go the opposite way. And there's no way for these two chlorine molecules to be facing each other in this way. Alright? Unlike here, the chlorine atoms are facing each other or are at the same side, and even if you rotate this, if you rotate it in such a way that this chlorine here goes down, the carbon here at the other side joins the rotation. So there's no way that you could turn this into this one unless you break this one. So the moment you break this one, you could rotate this part because there's no more pi bond. You could rotate this part without moving the other. Okay, so then it would exchange. Then you can return the double bond in some way so that you achieve something like this. So you have to break a bond also. That's configurational. But here we say that this is geometric. These are geometric isomers. So that applies to ones with pi bond and ones with cyclic bond. Let's have an example of geometric isomers which are cyclic, and let's see why they are geometric isomers. Well, I'll just draw cyclohexane. Alright. By the way, if they are in the same side, we should recall that they are, this one is different side. We say that this is trans, the trans isomer. And if they are in the same side, we call this cis. Well, look, there's no way that you could rotate the ring without